This is a tutorial on Halide, which is a programming language designed to make it much easier to write fast image processing code. These slides are meant to accompany and be interleaved with a set of interactive examples of writing and working with real Halide code. So in the live version of this tutorial, we alternate between discussing the core ideas in these slides and seeing them applied in real examples. For you reviewing this material online, you can flip back and forth between this talk and the completed commented examples on GitHub, which should be linked below. Here I'm going to start out giving a quick introduction to the big ideas in Halide and give a teaser of the kinds of results that you can get with it. And then in two later parts, I'll discuss some of the most important ideas as they've been set up in our initial code examples, specifically the two sides of how schedules are written. But for now, let's look at the big picture. Now, our initial motivation in building Halide is all around us. So the world is littered with cameras, and almost everyone is bolted directly to a powerful computer. My iPhone, for example, has an 8-megapixel main camera and tens to hundreds of gigaflops of peak parallel compute on both its ARM CPUs and its GPU. That's less than a PC, but it's still hundreds of flops per pixel of camera resolution. But if you want to process video in real time, it only has the bandwidth to read or write those pixels a couple of times in main memory. It's an amazing opportunity for software, but it requires lots of optimization of both parallelism and locality to actually exploit this hardware at anything like its peak capability. Now, if any of us wants to make real-time vision algorithms for a mobile camera, what are the practical options we have for writing this sort of code today? We'd usually like to write things like MATLAB, Python, or even simple modular C code, but doing that's not even close to efficient enough. So we have to break out tools like multi-threading, SIMD intrinsics, CUDA, or crazy abuses of OpenGL. And the reason for this is that there are lots of trade-offs essential to optimizing this type of code, which existing compilers can't make. So in practice, we have to write everything by hand with very low-level tools. We have to manually do things like parallelization, vectorization, and tiling. And we have to test lots of different applications of these ideas to see which ones actually work best, often rewriting all of our code in the process. And critically, building on optimized libraries like OpenCV and Intel Performance Primitives isn't enough either. And that's because while the individual operations in these libraries may be highly optimized, individually optimized kernels still compose into inefficient pipelines on modern machines, since they can't interleave multiple stages for locality across function calls. We show several times in our linked code examples how we can outperform OpenCV by up to 6 times in even relatively simple pipelines, using code that's simple enough to write in just a few minutes and a few tens of lines. So to put the challenges of high-performance image processing in concrete perspective, local Laplacian filters is a processing pipeline that's used heavily in Photoshop. It's used for HDR tone mapping and the clarity filter. And Adobe's version was written by one of their best developers in about 1,500 lines of optimized C++. It's manually multi-threaded and hand-coded for SSE. And it took him about 3 months to implement and optimize. And all that manual effort matters. The optimized version is 10 times faster than a reference version in about 300 lines of C++. So just porting your MATLAB code to C, while it can feel like a big speed up, usually isn't nearly enough to approach peak performance on a modern machine. It can easily be an order of magnitude still behind peak. And this isn't just about cameras and pretty pictures. Imaging is everywhere today, as many people viewing this well know. So most complex sensing today uses imaging somewhere under the hood, and it all needs more and more computation. But let's look at a simpler example. If we want to do a simple 2-pass box filter, we could write C++ code like this. It's just 2 sets of loops over the image where the first computes a horizontal blur and stores it in a buffer, and then the second vertically blurs that to produce the output. A hand-optimized version of this is over an order of magnitude faster. It's parallel, vectorized, tiled, and fused. We had to restructure the loops, introduce redundant computation on the tile boundaries, and change the data layout. I'd argue it's a complete mess, given that all we're doing is averaging 3 by 3 pixels. But under the covers, it's really just the same basic algorithm reorganized to optimize for parallelism and locality. Currently, no off-the-shelf compilers can do this full transformation, so you have to do it by hand. It's expensive and time-consuming, and the choice of the best transformations often isn't predictable or portable across architectures. Now, with Halide, we believe the right way to write this kind of code is to decouple the definition of the algorithm from the concerns of locality and parallelism, which we call the schedule. So in Halide, the algorithm defines what values are computed for each pipeline stage, while the schedule defines where and when they get computed. This makes it easier for you, the programmer, to write algorithms with lots of unnecessary details stripped away, and then to compose them into pipelines. It makes it easy to specify and explore different optimizations. Unlike in C, changing the schedule cannot change the meaning of the algorithm. And then it leaves the compiler free to do the painful but deterministic work of generating fast code, which implements the pipeline given a defined schedule. So once we strip out the concerns of scheduling, the algorithm is defined as a series of functions from pixel coordinates to expressions giving the values of those coordinates. The resulting code looks like this for the 3x3 blur. So here the first stage blur x is just defined at any point xy as the average of 3 points in the input. And then blur y is the average of 3 points in blur x. These functions have no side effects. They can be evaluated anywhere in an infinite domain. So x and y can range from negative to positive infinity, and these are still well defined. And then the required region of each stage is inferred by the compiler based on how much of the output you actually want. Now the execution order and storage of these operations are unspecified. So points in these functions can be evaluated in any order. The results can be cached, duplicated, thrown away, or recomputed without changing the meaning. You'll see more details on this algorithm language in the code examples, but for now the key point is that where in C we'd write loops, in Halide we write pure functions in terms of free variables over their domain and the evaluation of other functions. The specific scope of this programming model is what lets us have lots of flexibility in scheduling. So first, we only model functions over regular grids. That means Halide's a poor fit for irregular data structures like you might use in something like bundle adjustment, KD tree nearest neighbor algorithm, or other things like that. Second, we focus on feed-forward pipelines. So we can express recursive functions and reductions, but these have to have bounded depth at the time they're invoked. These constraints mean that our programming model is not technically Turing complete because we'd need potentially infinite-sized pipelines to express arbitrary complexity computations. And in practice, this means you can't write things like the outer loop of a dynamically terminating iterative algorithm, something like a conjugate gradient solver, in Halide. You can still write, and we do this in practice, the body of an optimization loop in Halide, or some unrolled set of iterations of the optimization loop. But the outer loop, which dynamically terminates based on some convergence condition, would still have to be in C or your favorite other host language. So that was the algorithm language. Now what about schedules? We'll spend a fair amount of time talking about this part of the language in the rest of this tutorial, but at a high level, these are what actually transform your code in different ways to determine the order of execution and placement of data. And this is where we'll deal with things like parallelism, vectorization, and locality. The implementation of Halide is an embedded DSL in C++. That means Halide programs are actually just C++ programs, but where the Halide algorithm is described using a few special types and functions we introduce. And it's then fed through our compiler to generate the actual optimized code. It uses LLVM for code generation. So at a high level, to compile a pipeline, we take the Halide functions in the schedule and use them to synthesize a set of loop nests and allocations, describing the whole fused pipeline for a given architecture. After our own vectorization pass and other optimizations, we pass it to LLVM to compile into vectorized x86 or ARM code, or to CUDA or OpenCL kernels, and the x86 or other CPU host code, including the logic to launch and manage them. In that last case, on the GPU, we can actually generate heterogeneous mixtures of vectorized multi-threaded CPU code intertwined with potentially many different GPU kernels based on the structure defined in the schedule. So over the past 2 years, we've also added backends for OpenCL, which I already alluded to, OpenGL ES, which is useful on mobile phones where compute APIs often don't exist for the GPU, native client, which can run in the browser, CSource, which is useful for potentially porting to other targets, and a variety of other things, including RenderScript. JavaScript and Metal backends are also in various stages of development. And in general, there's interest in targeting a whole bunch of different architectures. So now to give a sense of what this can let you do, local Laplacian filters, which I showed earlier, is used heavily in Photoshop. Remember, Adobe's version was originally 1,500 lines of hand-tuned C in assembly, and it took about 3 months to build and optimize. In comparison, a few years ago, I took a single day to rewrite it in Halide. It took 25 times less code and ran twice as fast as their optimized version on the same 8-core machine. At the same time, Adobe's also interested in GPU acceleration, but they're constrained by the cost of rewriting and optimizing thousands of lines of code. But from the same Halide algorithm, just changing a few lines of its schedule, we also generated a GPU version that was 9 times faster. Now, our implementations didn't just make a few extra optimizations. These weren't just low-level tweaks in some clever spot. They actually had to fuse and schedule each of 100 stages differently to globally balance parallelism, locality, and the total amount of work over the whole pipeline. In a language like C, these different schedules would have required changing essentially every loop in the whole program, rewriting hundreds or thousands of lines of code. And in this case, the best organization of this pipeline was just too hard for the original developer to find. So he stopped after 3 months of rewriting and optimizing for a specific machine. But with Halide, it was orders of magnitude easier both to express the algorithm and change the schedule. So he could try many more organizations in one afternoon than he could try in days or weeks of tuning. And this is just one of the applications we've explored. In the public research and open source code, we compared Halide versions of a range of imaging pipelines, from a couple to over 100 stages, to the best existing expert-tuned equivalents across x86 and ARM multi-cores as well as GPUs. And in all cases that we've seriously looked at, the Halide versions were both faster and dramatically less code. These days, we even have public pure Halide implementations of some highly optimized libraries. So in a very small amount of code, on the order of tens to hundreds of lines, you can write a faster Gaussian blur than OpenCV or IPP, which we show in an actual code example linked here, a faster FFT than FFTW, or a faster matrix multiply than Eigen. You can find all of these in our open source repository, and like I said, the live coding examples from this tutorial actually include a simplified version of the blur. And Halide's already being used pretty heavily in the real world. So our implementation's open source under a permissive license and is being actively developed in collaboration with people at Google, Adobe, and elsewhere. And people are already using it in multiple teams in a number of different companies. Most visibly at Google, there are currently dozens of engineers writing image processing code in Halide, and tens of thousands of lines of Halide code in production. The single biggest user inside of Google is Google Photos, which was recently relaunched at Google I/O. Their auto-enhance pipeline, for example, is written in Halide, so every time you upload a photo to Google on a variety of their different services, a bunch of Halide code runs in a data center somewhere. On Android and iOS phones, there's also a ton of Halide code. A stock Nexus 5 or 6 has over 100 different Halide pipelines built into it, and dozens more in popular apps on the iOS and Android app stores. So now we want to jump off to the initial examples and start writing some actual Halide code. You should go check out the Brighton example to see a basic Halide program in action. That example ends with a schedule discussed in the comments, which I'll unpack a little more here next, but you should go review and maybe compile and try running the code yourself before coming back. So to understand the schedule for that simple Brighton pipeline example, I want to show in a bit more detail and a bit more conceptually what the Halide schedule actually does. So Halide schedule defines the organization of computation in an image processing pipeline by specifying two things. First, for each stage, in what order should we compute its values? Remember, we're computing whole grids of pixels for each of these functions, so in what order should we compute the points in each of these grids? We call this part of the schedule the domain order, and it includes things like parallelization, vectorization, unrolling, and tiling. Now, second, when should we compute the pieces of each stage's inputs, or what granularity? This defines the interleaving of evaluation between producers and consumers in the pipeline, which determines the locality that we can exploit. Now, effectively, what we've done here is create a language as part of Halide for modeling the space of scheduling choices. And composing these choices in different ways for different stages makes different optimization trade-offs globally for an entire pipeline. So within each stage, we could, for example, process sequentially across Y and then sequentially across X, giving a simple scanline order. We can compute the X dimension in 4 wide vectors. We can distribute scanlines across parallel threads. Or finally, we can split the X and Y dimensions and separately control the outer and inner components of each. So then by reordering the split dimensions, we can get a simple tiled or Z-order traversal. Now what all these choices actually do is specify a loop nest to traverse the required region of each function. So the Brighton function that you should have seen in the initial example had 3 dimensions, x, y, c. The default order that you get, not specifying any schedule in the code, is to sequentially compute each dimension with the rightmost dimension in the function definition as the outermost loop. So in this case, that corresponds to a basic row major loop nest, going sequentially across each scan line before moving on to the next, inside an outer loop over color channels. Now the actual commands you can apply are first parallel, which marks a dimension to be computed by multiple parallel threads. And this is similar to an OpenMP parallel 4 pragma on that dimension. Internally, this uses a task queue implementation, so you don't need to worry about only parallelizing a loop with a number of iterations that matches the number of threads in your machine. Next, you can apply the command vectorize, which marks a dimension to be vectorized by a given width. This creates a new inner loop, which will ultimately be replaced by an 8-wide vector version of the loop body. Unroll similarly marks a dimension to be unrolled by a given width. This is basically the same as what we did with vectorize, but instead of generating vector code, it'll create, in this case, 4 copies of the loop body. Split takes 1 dimension and splits it into 2 new dimensions by a given factor. So here we can tile the Y dimension into segments of 64. And finally, reorder, which takes a list of dimensions and changes their relative loop nesting order. So here we pulled the loop over color channels inside the outer Y loop. There are also other commands available as syntactic sugar on top of these, for example, to easily tile a function in a single step, and also other operations related to storage layout and a variety of other things. But these are the most fundamental operations in the domain order that you want to understand. So now you can review what we actually did in the Brighton code with its schedule. You should be able to understand what all those operations written in the schedule section of that example do in terms of what I just described. Next, you should start reviewing the Gaussian blur example and come back here to understand how to schedule this multi-stage pipeline. So the part of the schedule I already discussed was the domain order, or in what order should we compute the values inside a given function. And that included splitting, vectorizing, parallelizing, etc. Now, the other thing the schedule is responsible for, which you start to hit in the blur example when you have multiple different stages sequentially composed together, is when should we compute pieces of each function's inputs, or at what granularity. And this defines the interleaving of evaluation between functions in the pipeline, which determines the locality that we can exploit. So it's easier to understand the possible transformations here if we look at an algorithm as a pipeline, as well as its corresponding loops. So the Gaussian blur pipeline looks like this, with the input flowing down through blur Y and blur X stages below. And these are the actual pixels on the left. So then, for each of these stages, we have some loop over its domain, which computes the pixels within a piece of that stage as required. So what's significant here is not what happens within each stage, within each of these loops. That's what we controlled with the domain order before. But now we want to look at what happens across the stages, or how these two sets of loops are combined to compute the whole pipeline. So starting out in the simple blur pipeline, you can use the default schedule, which inlines each function into all of its uses. So in this case, it just replaces every use of blur y inside the computation of blur x with the fully expanded implementation of blur y. This gives a single loop nest to compute blur x, or the output of the whole pipeline, but where the inner computation has exploded to evaluate the full 7x7 filter over the input. And this is what that actually looks like running. So for every pixel in blur x, it computes the 7 pixels it needs of blur y on demand immediately before using them. In this view, the yellow highlights show the pixel currently being computed, while the blue highlights show the values being loaded by that computation. If we step through one pixel at a time, you can see that one iteration of this loop computes 7 horizontally neighboring values of blur x, or blur y, each loading a 7 pixel tall strip of the input, and then combine those seven values of blur y to compute 1 pixel of blur x. And it's difficult for me to show here, given some keynote limitations, but you should feel free to pause and single step the video here to see a little more slowly in more detail what each of these operations is doing. Now this approach, this schedule has great locality. We're computing values of blur y on demand right when they're needed by blur x. So there's we basically maximized the producer-consumer locality between those two stages. And we can easily keep these values around in the L1 cache, or in this case even in registers, between where they're computed in blur y, the orange stage in the middle, and where they're used in blur x, the final purple stage. The problem here is that sticking the computation of blur y all the way inside the inner loop of blur x throws away and redundantly recomputes values that are needed by multiple iterations of this loop. So each time we go to compute the next pixel of blur x, we're sliding the kernel over by 1 pixel and recomputing 6 of the same pixels of blur y. We've basically turned our nice separable 7-tap filters into a dense 2D 49-tap filter, doing 7 times as much work as we need to. At the other extreme, compute root, which you should try yourself in the code example, pulls the computation of blur y entirely outside the computation of blur x. So in this case, we get a complete loop nest to compute all of blur y before computing any of blur x. Running that looks like this. It computes everything we're ever going to need in blur y before computing any of blur x. So by the time we get around to computing anything in blur x, we're only reading the values in blur y since they're already computed ahead of time. But by the time we do read any of these values, we've computed an entire image of other values in between. So these intermediate values from blur y will have been kicked out of any cache, written all the way back to main memory, from which we'll have to slowly read them all back in. So far we've put the orange loop nest that computes blur y all the way inside the computation of each point of blur x with inline, or all the way outside with compute root. So where else could we put this orange computation relative to the purple computation? Now in Halide, we also let you choose any level of the loop nest of the consumer function, in this case blur x, is a granularity at which to compute the producer function, in this case blur y. So I can pick any level in these loops over blur x at which I want to compute blur y. So before, by fully inlining, we shoved it all the way inside, which introduced lots of redundant compute. But what's the farthest in we could push it? The closest we can push blur x to its use in blur y, or sorry, closest we can push blur y to its use in blur x without introducing any redundant computation. If we compute blur y at the y iterations of blur x, we get a loop nest like this. And what about the bounds of these loops? In Halide, you don't specify the bounds of the loops. They're inferred by the compiler based on context. So the compiler says, at this granularity, how much of blur y is needed for each of these iterations of blur x. In this case, a single scanline of blur x only needs a single scanline of blur y. So we don't even need loops over the c and y dimensions of blur y in this case. And this is what that actually looks like running. So you can see here, for every scanline of blur x, we first compute a scanline of blur y and then immediately consume it to compute the corresponding scanline of blur x. And then we can throw it away and move on to the next. So this has good locality. quickly switching back and forth at the granularity of just a single scan line instead of a whole image. In this case, actually, it's a single scan line of a single color channel as opposed to a whole three color channel image. But it does no redundant computation. Each value in blur Y is computed exactly once, and reused at the level of reused within a scan line under the filter kernel of blur X. And if you look at the actual performance of this in the running code, you'll see that it's several times faster than even a fully parallelized vectorized version scheduled either compute root or inline. And that's because it's minimized redundant computation, in this case cut it down to nothing, while still getting, it's still exposing enough locality to operate efficiently out of the cache instead of needing to go to and from main memory. So don't take my word for it. Now you should definitely go run the final schedule in our Gaussian blur example code and see how it actually performs on your machine. And feel free to experiment also with different potential organizations and see how they perform. This is a relatively simple example, and we actually often find that a pretty wide range of different, somewhat related schedules often have very similar performance. Basically, once you get up to the level of being either compute limited or bandwidth limited, fundamentally on a given pipeline like this, you'll find you can hit peak performance in a variety of different ways. And this is just one relatively idiomatic way that we found with just a few lines of schedule to make this go fast. But you can probably explore a variety of others, some of which may surprise you and not go as fast as you think, and others of which may be able to match the performance of this using loop nests that actually look quite different. But the great thing about Halide, of course, is that you can trial this stuff, see how it actually pans out in a matter of seconds just by changing a couple of lines instead of restructuring and rejiggering a whole bunch of interleaf loop nests, having to worry about changing boundary conditions, changing memory allocations, changing indexing schemes, etc. So it's very easy to experiment and explore the performance space for a given program. So that's it for these slides, but you should definitely go check out both the later examples in the example code repository, which do include all of the other things discussed on this agenda slide, as well as all the tutorials. There's a series of similarly commented tutorials building up from very simple examples similar to the Brighton example up through exploring a variety of concepts in scheduling and other things in the main Halide repository under the tutorials directory. Thanks.